Okay, I wanted to start with a magic trick. So I've got 5 empty beakers here. I'm going to take this one and fill it with some water from the sink. Just a little bit. So just some water in here. And I'm going to pour that into this first beaker. That's kind of cool. Okay, then it turns pink. Pretty neat little reaction. I'm going to top this off with a little bit more water from the sink. So just so you can see that I'm like filling it from the sink. I'll put it over here. So same beaker, take it, put a little bit more water into it, just so that it's kind of watered down. You're like, okay, that's not that cool, Miss Coulson. There's obviously something in that glass. But what I think is cool is this next part, when I take this and pour it into another empty beaker and that's actually kind of neat, huh? Okay. And then my next one, if I take it and I put it into the next empty beaker, hopefully if my magic calculations are correct, but I put this in here and, ooh, miscalculation there. But it was cool for a second, wasn't it? All right, back at it. I put a little bit more stuff in here so that I could continue pouring it, and then obviously it's going to stay pink. Good. Then, if I pour this, hopefully, maybe I mess up my concentrations now, it will turn back. Yeah, maybe just a little swirl, swirl, swirl. We'll try it. Okay, I'll say that stayed clear. That stayed like kind of clear. We'll take it. Just a little more. What we're doing is like almost like a large scale version of titration. So this is maybe a good introduction. The pink stuff that we're using is phenolphthalein, which is an indicator that is pink like this in the presence of a base, which is how I was able to do this. So right now, because it's kind of like turning pink and then clear and then pink and then clear, it's like pretty close, I'd say, to the point of neutralization, which is not the purpose of a titration, but that helps you to figure out, if I was actually measuring the volume of each of these, what the concentration is of each of these, my base and my acid. So in the pink solution, that is indicating that this is a basic solution right now. Anytime that it was clear, that was indicating that it was an acid. Okay, so all magic stuff aside, here is kind of our setup that we're working with, just to give you a little orientation. So we've obviously got our Erlenmeyer flask, and it's sitting on top of a hot plate. So this is finally when we're using the stir function that y'all have asked about all year long. So the heat is all the way off. There's no heat on, but that little stir thing is about to be used. So if I put this back up here, sorry if you get motion sickness. Okay, if I turn on my stir function, there's a little magnet in here. That's what this white piece is, if you can see that. And so that sticks to this, and I can turn it on and start. If you center it, so the magnet is like sticking to the center of the magnet inside the hot plate or stir thing, whatever. And it was hitting the side of the glass because it wasn't centered, so I just centered it, and that's what made the noise stop. And then meanwhile, what we have set up above this is a burette. I put this white thing behind it just so you can see the color better once that happens. So inside my burette, I have a known volume. Normally you would go all the way to the top, but I've already been doing this, and I know that I don't need the whole thing. So your burette like this, and have a known volume of a base with a known concentration in there. So what we have in this one is 0.7 molar sodium hydroxide. So then what I do, if I can turn this actually, I think I should be able to, it'll be fine. So if I turn this, I just turned the burette, you didn't see it, but this thing, I don't remember what they called it in the video or in little Professor Patel's online simulation, but we call this the stopcock usually, and basically if it's perpendicular, sorry you can't see it, perpendicular to the rest of the burette, then it's closed, and as you turn it, like just a tiny, tiny, tiny little bit, it starts to open up. And so the goal is to open it so that you're at like a comfortable drip. So I'm going to keep on turning it super slowly. The more vertical it gets, slash parallel, like parallel to the rest of the burette, the more open it is. Ooh, so that let out like a steady stream. I did not want that. That's too much. So a little less. It's really hard to see it because it's like a tiny little thin stream. Maybe you can see that? You see the little drip about to come out? Okay, so we'll let the drops start going. So now it's dripping at a steady rate, and it's something manageable where I can see it. And what's happening is as it's hitting this, oh, what I didn't say is I have a known volume with unknown concentration of acid inside my Erlenmeyer flask already. So that's what's spinning. And so as this is going, it's not happening right now, but actually you can kind of see it. Little flashes of pink appear because there's also phenolphthalein in the bottom. So that is the stuff that we were just using to indicate a base. So since I have a base in my burette and an acid down in my flask solution is primarily acidic, or it is completely acidic right now, but every time a drop of the base hits it, that base is in contact with the indicators. So if you can kind of see it like flashing pink, you're not imagining things. So it's pink and then it'll go away, and pink and it'll go away. So we'll just kind of let that keep running. I'll set this here. We could also drip it faster. So what you did in the online simulation is you did multiple trials so that you could, instead of having it drip, 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 drip for who knows how long, you did kind of like a rough estimation at first. That way you had a range of, okay, between 10 and 14 milliliters is when it's going to change colors. That way you could get it to like 9 milliliters really quickly, and then start the drip. So what's happening right now is as it's dripping, the level in the burette is of course going down, but it's going down super, super slowly. I can tell it's starting to sort of be pinkish for a little bit longer, so I'm going to just leave it. No, I'm impatient. I'm going to try to speed it up just a bit. Okay, there we go. So it's still just dripping, but it's dripping faster so that you can see the rate if I go up here. So dripping a little bit faster. So if you can tell, with every drop that's happening, just a little bit of pink is showing up in here. And so similar to the little magic trick experiment, whatever you want to call it, that I did at the beginning of the video, it will like turn pink and then go back to clear. So we are going to find the point of neutralization when it turns pink and stays pink. Keep going. So now it's becoming a lot more obvious that the pink drips are happening. And so if I want this to happen slower, I can turn my little drip rate down. So all I'm doing is off screen, but I'm just turning the stopcock so that it's less open. So it's dripping slower. I'll turn it on a little faster, but you'll be able to see every single drip that goes in there turns it pink, and then it turns clear again. So using this method, you're able to get a really precise reading because you know down to the very drop how much of that base of a known molarity or known strength, known concentration, not strength, don't say strength, sorry. A known molarity is how much of that it takes to neutralize this acid. It is really important to be patient. I know we're just kind of sitting here quietly watching it, but it's important to be patient with it because if I turn it up and I start putting the drops in faster, you'll likely go over the amount that you actually needed, and it doesn't give you a good reading. And then I am really impatient. I just want to drip, drip, drip a little faster. Just a touch. But you see, if I have it dripping just a little bit faster, it's hard to tell when the pink fully disappears versus when it's like starting to kind of turn the pink turn the solution pink, I mean. Do that, boom, boom, boom. Just a little faster. So if I turn it off and it's spinning, you see the pink still goes away. So I put maybe just like a quick little stream. So I'll put it up here so you can kind of see what's happening. So you see the pink is kind of lingering a little bit longer with that extra little hit of... Did I go over? I hope not. Almost. Okay, so you see the pink is lingering for longer, but as it's mixing, it's still going away. So that means that the solution that's in my Erlenmeyer flask is still acidic, since the indicator, the phenolphthalein, is not showing that it indicates a base. So that is a little too close for comfort for me, so I'm going to bring it back down to the drip rate. A little slower. But again, because the pink is lingering for longer, that tells me that we're getting closer to that point that we're looking for. So that solution is like almost pink. I don't know if you can tell as well as I can up here, but let me try to move that around. It's like a pinky clear sort of color. So it's like got tiny, tiny little bit of pigment in there. One drop, let's see what happens. Same thing, so it's not very pigmented, but you can kind of tell that it's not fully clear. I'm not sure how well that's going to translate on the video. So I'm just going drop by drop right now. So it's still turning white, okay, or clear. Keep going. That pink is just because it splashed a little bit. There it is with the sound again. Stop. Okay, so we're going to keep on going. 2 drops. Again, maybe, I think that pink is sort of starting to show up a little bit more, but what we want is for us to be able to see like that really vibrant magenta kind of color. But that is noticeably pinker too. It's like watered down pink. Again, a little bit pinker, but certainly not magenta. I almost messed it up, just putting too much in there. So definitely a light pink, but again, we want the full color change all the way. So this solution, the fact that I can see the pink at all does tell me that it's basic. So I would say somewhere in this general range would be your point of neutralization. So that's why we do multiple trials and we take the average of it just like you did in the online simulator. A couple more drops. It could be that I didn't have enough phenolphthalein in there, but I don't think that's the case because I'm seeing it get darker pink in here. So drip, drip, drip. So you can tell that's a lot darker. So at this point, I would say that the solution has changed from acidic to basic, which means that we were like maybe 3 or 4 drops away from our point of neutralization on there. If I stir it a little faster, so I'm just turning up the stir thing. I'm just trying to see if it'll lighten. So the color actually is a little lighter. Why not? Since we're not really measuring anything in here, I'm just going to put more in and see how much darker the color gets. Okay, so you can tell it's actually noticeably darker like this. So again, there's kind of a range of where it actually changes color because you want it to get to the point where it is very vibrant, very noticeable, very pigmented. And then once you have it, that color, I could just keep on adding more and it's not going to get any darker pink. Like that color pink is what we're looking for. So the light pink at the beginning, I maybe stopped it a little bit early, but again, any pink at all indicates that a base is present. So that light color pink tells me that I was able to stop it really, really close to the point of neutralization. I'm going to go ahead and turn off my spinner. Some of my students liked this yesterday. My little hack for getting the magnet out without having to touch it is that if you take this, not that it really matters, but I've got my magnet, and if I take another magnet and put it on the bottom, and then I turn you around, oops, and pour this down the sink with the magnet on there still, then I'm left with my magnets like that. So not too bad, and then I can rinse this, oops, and then retrieve my magnet without like touching any kind of chemicals, especially once I started adding way too much of the base and it got that super bright pink color. We don't really know how strong it is because I wasn't measuring it. You should know how strong it is because in real life, when you're really doing a titration, the point is to measure it, which kind of brings me to the point of going through all of this. What is the point of a titration? If you're not sure, you should maybe go back and review the titration simulation online that we were doing, but the point of a titration is to figure out the molarity or the concentration of a known volume of an acid or a base. So we could do this basically the same setup in reverse, where we could have, instead of having a base in our burette and an acid in our Erlenmeyer flask, we could flip that and have the acid in the acid in the burette and a base in the Erlenmeyer flask. But if we did it that way, we would need a different kind of indicator most likely, just because it would, well, I mean, I guess we could use phenolphthalein still. It would just be the absence of color that we're looking for. So the point is to be able to figure out the concentration of something that you don't know the concentration of using a known volume and known concentration of something else. So I wanted to make sure that y'all know how to do this kind of problem. So I wrote out if it only takes 5 milliliters of 6 molar acid to neutralize 30 milliliters. Ooh, this is messed up. Hold on, let me fix it and then I'll come back to it. All right, sorry about that. I wasn't about to redo the whole video just because of my quick little mistake in typing this up. But if it only takes 5 milliliters of a 6 molar base to neutralize 22 milliliters of acid, what is the concentration of the acid? So this is basically the kind of setup that we just had, where if you can imagine in your burette, you've got your base, and you'll know that this is the one that's in the burette because this is what you're trying to figure out how much of it takes. That's how you would be able to figure out how much it takes to neutralize it. So then you've got your 22 milliliters of acid down here. We'll call it HCl because that's what we just used. So my base, and then in your burette you've got 5 milliliters, so just a very little amount. Doesn't mean you actually have that much in there, it just means that's how much it took for it to be able to be neutralized, and you know that this is a 6 molar concentration, and what we're trying to figure out is what is the concentration of the acid. So I'm looking for my molarity of the acid. If you caught it, I corrected myself when I talked about the strength of the acid. We talk about concentration and strength in like informal settings as the same thing, but in regards to acids, they are not the same thing. So our strong acids are going to be strong acids because they completely dissociate, not because they have a high concentration or a high molarity. So that terminology was incorrect when I said that before. But this equation should look familiar to you because we just came from our solutions unit. We're going to use the exact same equation, but I went ahead and rewrote it with A and B for acid and base. So you know that the molarity of your acid times the volume of your acid is equivalent to the molarity of your base times the volume of your base. If I'm looking for the molarity of my acid, then I'm looking for MA, so I'm going to just keep that as MA. I would multiply that by the volume of my acid. This is in milliliters, and this is also in milliliters, so I don't need to convert, but you could if you really wanted to. You could write them both as liters. As long as it matches on both sides of the equation, the math will work out the same. So 22 milliliters is my volume, and then my molarity of my base is 6 molar times the volume of my base, which is just 5 milliliters. So 6 times 5, you'll notice I also changed this because I just picked random numbers, and then the first version of this I had 30, and I didn't really like that it came out to 1 molar. I wanted something a little different. So my molarity of my acid is going to equal 6 times 5, which is 30, divided by 22. So I did that by dividing that, get rid of 22, get rid of 22. Okay. And then 30 divided by 22 in your calculator gives me that my acid had a molarity of 1.36. And as far as significant figures, it would, I guess, just have 1 sig fig, so really it would still be called a 1 molar acid. But probably if we were asking a question this specific, I would have added like 0.00 on the end. So 1.36, just so that it's similar rounding to what we did before. Otherwise, of course, significant figures matter. So hopefully this helps you and you're not overthinking this kind of calculation question.